So let's consider the case where the transmission line is not infinite and actually ends somewhere. So we have a transmission line and you have all of the inductances. And let's say this ends in an open circuit. So I'm going to draw the other side here, the other conductor, open circuit, and capacitor, 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 capacitor. And bear in mind, I'm drawing these as actual lumped elements here as capacitors and inductors. This would only be a true transmission line if the length of each of these sections, if you took the limit as each of these sections shrunk and became infinitely small, and then each of this would be a distributed capacitance, distributed inductance over the length of the transmission line. So this is, I've drawn out here a lumped element approximation of a transmission line. And so how does this behave? Well, we're going to have, your voltage wave propagating, current wave propagating. Just going to charge everything up. Just going to moving forward. And then it suddenly reaches the end. And at this point, the current cannot move further because there's no path for it to continue flowing. It can't flow through the open circuit. And so at this point, there would be a decrease in current, but the inductors don't want a decrease in current because inductors resist changes in current. So what they're going to do, what each inductor, which has been charged up, is going to do, is it's going to discharge into the capacitors. And so this capacitor is going to actually acquire twice the initial charge from the charge that's just being dumped onto it by the inductor. And then this next one will do the same thing. It'll charge the capacitor up to twice this value. And from the end back to the beginning, each of the capacitors is going to be charged up by the current that's being dumped onto it from the inductors. And so and then eventually the current wave reaches the beginning, and then that's the end of the signal propagation in this transmission line. You had this initial wave, which we call the incident wave, which is the initial forward moving wave of voltage and current. And then you have almost another wave that's propagating from the end back to the beginning that's equal to the original wave. This is the reflected wave. It's almost as if that incident wave bounced back from the end of the transmission line from that open circuit, going back through the transmission line, back to the source, charging everything up again to twice the initial value. And so it's almost like there was a reflection at that point. And so what you're left with at the end is a voltage across these two terminals, but no current. And so that's the definition of an open circuit. An open circuit is where you have a voltage, but some voltage, but no current. And so this is what you would expect. If you took like a battery and connected two wires to it that weren't connected to each other at the other end, you would expect there to be an open circuit with the voltage, but no current flow. So after you have this initial incident wave and then the reflected wave propagating on a transmission line, that is what you see. What if these were shorted to each other? What if you had a transmission line where you have your distributed inductance and there's a short, and then just draw the rest of the line. And so you have a short circuit at the end there. And so let's trace the voltage and current wave. So I'll just draw the voltage wave propagating forward. And then now once you reach the end, you see a short circuit where there's by definition 0 volts. A short circuit is where you can have some current, but 0 volts across it. And so now this last capacitor is going to, it's charged up, but it's going to want to discharge through this open circuit because you've just, through the short circuit, because you've just connected a wire across the leads of the capacitor. It's even better than an RC circuit. It's just going to straight up discharge through the short circuit. And so you're going to lose this voltage that's built up on the capacitor as it discharges. And so then this next capacitor down the line is also going to see this short circuit. And so it's going to also discharge and lose its voltage. And you'll also see this for all the previous ones. From the end back to the beginning, each capacitor will lose its voltage until you reach the beginning. And what you essentially see there will be current flow across this circuit, but there will be 0 volts across it, which is the definition of a short circuit. Which again, if you took a battery, connected a wire straight across the leads, that's what you would expect. There to be no voltage, but a whole lot of current if there was no current limiting components there. And so what you see in this case is there's an incident wave, then there's a reflected wave, except the reflected wave has the opposite polarity as the original wave. It's like the incident wave was inverted and then sent back from the short circuit, because the reflected wave canceled out the original wave. All the voltages in the first case, in the open circuit case, were doubled. Here they were canceled out, brought to 0. So it's like the reflected wave had the opposite polarity as the incident wave. Okay, one last case I want to talk about. Let's say you have I'll draw this out again just for fun. Oh, okay. Sorry. I have a quick mistake there. Okay, but whatever. Okay, so you have your transmission line. And it's terminated in a resistor. And this resistor has a specific resistance, which is Z0. Remember, the transmission line has a characteristic impedance Z0. It acts as a resistor with a value of Z0. And so this resistor now that we've terminated with has a value of Z0. And so what happens here? Well, you have your current propagating here, plus minus, charge building up, plus minus. So that just continues happening, plus minus, plus minus. And then you reach the resistor, and there's no difference to the voltage source perspective between what it's been seeing so far and what it's seeing now. You'll see a voltage built up across here. You'll see a current flowing across the resistor. But for that same voltage, you'll still see that same current that's been flowing all this time through the transmission line, because the resistor has the same impedance as the characteristic impedance of the transmission line. Again, from the voltage source perspective, there's no difference between a resistor of value Z0 and a transmission line with characteristic impedance, a lossless transmission line with characteristic impedance Z0. And so you see the wave sort of just stops here, but it continues flowing. And this is, again, the exact same as if you just had a battery and connected a resistor across the leads of the battery with a value of Z0. You see current flowing through this resistor, a voltage across this resistor. And so this transmission line is matched. You don't see any reflections coming back from this transmission line. The incident wave is sort of absorbed at this resistor, and you just keep the resistor just keeps drawing current. And so that's sort of this third case where the transmission line is matched.